Good day, Dr. Cecilio Baga, and good day, everyone. I'm the AI voice stand-in for today's presenter, Mr. RONALD MUSNI. On the menu, we have Topic 3.1, Properties of Materials, and Topic 3.2, Ferrous Metals. So, without further ado, find a comfortable spot, maybe grab your coffee, and let's dive in. I promise it'll be more fun than staring at a blank wall, and hopefully, you'll learn something new along the way. Let's get started. Engineering materials form the backbone of every man-made structure and device we rely on today. They are the foundation of engineered products, defining not only how something is built, but also how it functions and endures over time. From the steel that supports towering bridges, to the polymers that insulate electrical circuits, materials shape the world around us. These materials are crucial across multiple disciplines. In civil engineering, they enable the construction of bridges, buildings, and infrastructure. In mechanical engineering, they drive the performance of machinery, vehicles, and industrial systems. Electrical engineers depend on them for conductors, circuits, and insulating components. And in architecture, they ensure structural integrity while enhancing aesthetic appeal. But how do engineers choose the right material? It comes down to understanding the properties that drive performance and selection. A material's behavior, under different operating and environmental conditions, depends on its intrinsic characteristics. These can be physical, chemical, or mechanical properties, and they directly impact utility and performance. Key requirements often include strength, durability, conductivity, weight, toughness, hardness, and elasticity. By carefully matching these properties to the demands of a project, engineers ensure that the end project is both functional and enduring. Now, let us start with the mechanical properties. Mechanical properties reveal how a material responds when forces are applied. Forces that can stretch it, compress it, twist it, or try to break it apart. These characteristics are crucial in determining whether a material is suitable for a given structural or mechanical design. Strength is the material's ability to withstand loads without failure, whether in tension, compression, or shear. Hardness measures its resistance to scratching, abrasion, or indentation. Ductility is the capacity to deform under tensile stress. Imagine stretching metal into a thin wire, while malleability refers to its ability to deform under compressive stress, like shaping it into thin sheets. Toughness is about absorbing energy and deforming plastically without breaking, while brittleness is the opposite, the tendency to fracture easily under stress with little deformation. Elasticity is the ability to return to its original shape after the stress is removed, and plasticity is the ability to retain the deformation once the stress is gone. To measure these properties accurately, engineers use tools like the Universal Testing Machine, which quantifies key mechanical properties such as strength and ductility. Understanding these values ensures that each material chosen can meet the demands of its intended application. Moving on to the next, we have the physical properties, which describe measurable characteristics of a material that do not alter its chemical composition. They are essential for predicting how a material will behave under different conditions and environments, making them a key factor in determining a material's overall utility. One of the most important physical properties is density, the mass of a material per unit volume. Density plays a critical role in weight calculations for both components and large structures, directly affecting efficiency and influencing material costs. Another vital property is the melting point, the temperature at which a material transitions from a solid to a liquid state. This determines the upper limit of a material's operating temperature and is particularly important in manufacturing processes such as casting. where materials must withstand extreme heat without degrading prematurely. By understanding these physical properties, engineers can make informed decisions that ensure both the performance and cost-effectiveness of their designs. Then we have thermal conductivity, the ability of a material to transfer heat. From HVAC heat exchangers to advanced cooling systems, this property is vital where heat must move efficiently. High thermal conductivity keeps systems running smoothly, preventing overheating and maximizing performance. Then onto the electrical conductivity, which is a material's capacity to carry electric current. It's the heartbeat of modern electronics, from the copper wiring in our homes to the circuits in our devices. Without it, the flow of energy that powers our world would simply stop. Finally, thermal expansion, the way materials change in size when heated. Engineers must account for this property when building bridges, pipelines, and precision components. A small change in temperature can mean big stress on a structure if not properly managed. Understanding these properties isn't just science, it's the foundation of innovation. From keeping us warm in winter to lighting our cities, these material behaviors shape the technology and infrastructure we rely on every day. Now, let's move to chemical properties. Chemical properties describe how a material behaves and interacts with its environment, influencing its stability, durability, and safety over time. These characteristics are vital for determining a material's long-term performance in real-world conditions. As Sediono noted in 2015, chemical properties are among the key determinants of a material's overall utility. Corrosion resistance is the ability of a material to withstand chemical degradation, such as rust, caused by moisture or other environmental factors. This property is essential for materials used in marine, outdoor, or chemical processing environments. Oxidation resistance refers to how well a material tolerates reactions with oxygen, especially at elevated temperatures. This is critical for components that operate in extreme heat, such as engine parts, turbines, or furnace linings. Chemical stability measures a material's resistance to undergoing chemical change or decomposition under specific conditions. High stability ensures that a material remains reliable and functional over its intended lifespan. Flammability, on the other hand, assesses a material's tendency to ignite or burn when exposed to flame or heat. This is a vital safety consideration in engineering and design, particularly in applications where fire hazards must be minimized. By evaluating these chemical properties, engineers can choose materials that maintain their integrity, protect user safety, and deliver consistent performance over time. Next are thermal properties. Thermal properties describe how materials respond to heat and changes in temperature, determining whether they can withstand high heat environments or effectively insulate against them. These characteristics are critical for predicting performance, preventing deformation, and designing efficient thermal management systems. As noted in advanced engineering materials, enhancing thermal stability can dramatically improve a material's performance across a wide temperature range. Specific heat capacity measures the amount of heat energy required to raise the temperature of a unit mass of a material by 1 degree. This tells us how well a material can store heat. Materials with a high specific heat capacity are ideal for thermal energy storage, such as in solar thermal systems, and are often used as coolants to efficiently carry heat away from sensitive components. Thermal resistance, on the other hand, describes how strongly a material resists the flow of heat. High thermal resistance is essential for insulation, preventing unwanted heat transfer. Conversely, materials with low thermal resistance are used in heat sinks, where rapid heat dissipation is necessary to keep electronics and machinery cool. Heat distortion temperature indicates the temperature at which a polymer begins to deform under a specific load. This property is critical for ensuring that materials retain their stiffness in heated environments, such as automotive components or machinery housing. Selecting materials with a suitable heat distortion temperature ensures that products do not soften, warp, or fail under their operating conditions. By understanding and applying these thermal properties, engineers can design systems that perform reliably, manage heat efficiently, and withstand demanding temperature conditions. Next are the electrical properties. These properties are critical for electrical and electronic system design. Electrical properties define a material's response to electric fields and current flow. These characteristics are paramount for selecting materials used in a vast array of electrical and electronic applications, from power transmission to microprocessors. The efficiency, safety, and performance of any electrical or electronic system directly depend on the electrical properties of its constituent materials. An in-depth understanding ensures optimal functionality and reliability. Conductivity is the ability to carry electric current. High-conductivity metals like copper and silver allow charges to move with minimal resistance, powering everything from household wiring to computer circuit boards. Resistivity is the opposite. It measures how strongly a material resists electrical flow. High resistivity materials, like rubber or ceramic, are perfect for insulation, while controlled resistivity in alloys is used in heating elements, like tester coils. Dielectric strength measures how much electric field an insulating material can withstand before breaking down. It ensures safety in high-voltage components like capacitors, transformers, and heavy-duty power cables, preventing dangerous short circuits or arcing. Then we have the optical properties. This describes how materials interact with light, shaping both their appearance and their function in a wide range of modern technologies. These properties are at the heart of everything from high-performance cameras to advanced medical devices. Transparency is the ability of a material to let light pass through without significant scattering or absorption. This determines whether a material is transparent, translucent, or opaque, and it's essential for applications where clear vision or efficient light transmission is critical. Reflectivity measures how much light a material bounces back from its surface. It's expressed as a ratio and plays an important role in mirrors, protective coatings, and reducing glare on displays. The refractive index, on the other hand, tells us how much light bends when entering a material. This property is fundamental in the design of lenses, prisms, and fiber optics, allowing engineers to guide or focus light with precision. These optical characteristics fuel innovation across industries. In precision optics, specific refractive indices enable the creation of high-performance lenses for cameras, microscopes, and eyeglasses. In communication, outstanding transparency powers fiber optic cables for rapid, long-distance data transmission. In screens and displays, carefully balanced transparency and reflectivity ensure maximum brightness while minimizing glare. And in the medical field, tailored optical responses are crucial for diagnostic tools, surgical instruments, and advanced sensors. By mastering optical properties, engineers can create materials that not only look right, but perform brilliantly. Acoustic properties describe how materials interact with sound waves, shaping their ability to transmit, reflect, or absorb sound energy. These properties are vital for effective noise control and soundproofing, influencing comfort, communication, and safety in spaces ranging from quiet offices to busy industrial plants. One key acoustic property is sound absorption, the ability of a material to dampen sound waves by converting their energy into heat. This reduces reverberation and echo, making spaces more comfortable and improving sound quality. Materials like porous foams and acoustic panels are commonly used in auditoriums, offices, and recording studios to achieve these effects. The goal is to control noise within a space, improving clarity and reducing unwanted background noise. Another important factor is acoustic impedance, which measures a material's resistance to the passage of sound. This property determines how much sound is reflected versus transmitted at the boundary between two materials. Dense materials like concrete or mass-loaded vinyl often have high acoustic impedance, reflecting sound effectively and making them ideal for soundproofing. The greater the impedance mismatch between materials, the more sound is reflected, perfect for creating strong sound barriers. By understanding and applying these acoustic principles, engineers and designers can create environments that are quieter, clearer, and more acoustically balanced. And lastly, we have the manufacturing properties. These properties describe how a material behaves during industrial processing processes, like casting, welding, machining, and forming. Understanding these characteristics is crucial for selecting materials that can be shaped into finished products efficiently, cost-effectively, and without defects, directly influencing both production yield and final quality. Castability is the ease with which a material can be shaped by pouring it into a mold. Materials with good castability flow smoothly, shrink minimally, and resist defects, making them ideal for intricate or high-volume casting operations. Weldability refers to a material's ability to be joined through welding without forming cracks or other defects, while still maintaining strong and reliable mechanical properties in the welded joint. Machinability is the ease with which a material can be cut, drilled, or shaped using chip removal processes. Good machinability means longer tool life, better surface finishes, and lower power consumption, all essential for achieving precision manufacturing at lower costs. Formability is the ability of a material to be bent, stamped, or otherwise deformed into desired shapes without breaking or failing. This property is vital for processes like sheet metal forming and forging, where the material must withstand significant reshaping. By carefully considering manufacturing properties, engineers ensure that chosen materials not only meet performance requirements in the final product, but also fit seamlessly into the production process. In conclusion, mastering the science of materials is the cornerstone of creating better, safer, and more efficient products. By understanding material properties, engineers can optimize designs, significantly boosting performance and ensuring that every component functions as intended. Proper material selection is not just about performance, it's also about safety and cost-effectiveness. The right choice prevents failures, improves reliability, and reduces long-term expenses across all engineering applications. True engineering success requires a holistic view, one that considers the interplay of mechanical, physical, thermal, and chemical properties. No single characteristic exists in isolation. Effective solutions come from balancing them all. Ultimately, the right combination of material properties is the key to innovation. It drives efficiency, inspires new technologies, and lays the foundation for groundbreaking advancements that shape the future of engineering. Let us now proceed to topic 3.2, the ferrous metals, understanding their types, properties, and applications. Let's get it on. Ferrous metals are those that contain iron as their primary element. They form the backbone of countless industries, from engineering and construction to automotive manufacturing and large-scale infrastructure projects. Their popularity stems from a combination of exceptional strength, impressive durability, and distinctive magnetic properties. The behavior and performance of ferrous metals aren't determined by iron alone. The presence of carbon, along with other alloying elements, plays a significant role in shaping their characteristics. By adjusting these elements, engineers can fine-tune properties such as hardness, toughness, corrosion resistance, and machinability, ensuring the right metal for the right job. From towering skyscrapers to precision-engineered automotive parts, ferrous metals remain an essential material in building the modern world. Ferrous metals fall into two main groups: pure iron and iron alloys, each with unique characteristics. Pure iron has extremely low carbon content and distinct softness, but limited structural use. Wrought iron, with less than 0.8% carbon and fibrous slag, is highly ductile, malleable, and fatigue-resistant, often used in gates, railings, and heritage structures. Commercially pure iron, with minimal impurities, offers excellent magnetic properties and good electrical conductivity for specialized industrial uses. Iron alloys are created by combining iron with carbon and other elements to enhance strength, hardness, and corrosion resistance. Steel, with up to about 2% carbon, is strong, ductile, and versatile, while cast iron, with 2 to 4% carbon, provides excellent castability and compressive strength, but is more brittle, making it ideal for engine blocks, pipes, and machinery bases. Each classification plays a vital role in engineering, construction, and manufacturing. Together, these classifications of ferrous metals form the foundation of modern industry, with each type serving a unique role in engineering and manufacturing. Carbon steel is one of the most important ferrous metals, valued for its strength, versatility, and wide range of applications. It is an alloy of iron and carbon, with carbon content dictating its hardness, strength, and ductility. Low carbon steel, with 0.05% to 0.30% carbon, is highly ductile, malleable, and easy to form or weld, making it ideal for structural parts, wires, pipes, and automotive panels. Medium carbon steel, containing 0.30% to 0.60% carbon, balances strength, hardness, and ductility, and can be heat-treated for added performance. It's used for axles, gears, crankshafts, and machinery components. High carbon steel, with 0.60% to 1.5% carbon, offers exceptional hardness and wear resistance, but is more brittle. It's best suited for knives, drills, springs, and high-strength wires. By adjusting carbon content, carbon steels can be tailored for uses ranging from flexible structures to heavy-duty tools. Alloy steels are enhanced with elements like chromium, nickel, and molybdenum to improve performance beyond that of carbon steel. Low alloy steel contains up to 8% alloying elements, offering better strength, toughness, and wear resistance. It's widely used for pipelines, pressure vessels, gears, and automotive parts. High alloy steel, most notably stainless steel, contains over 10.5% chromium for superior corrosion resistance, heat tolerance, and a non-staining finish. This makes it ideal for kitchenware, surgical instruments, and chemical processing equipment. Special-purpose steels are designed for specific demands. Tool steel is extremely hard and wear-resistant, perfect for cutting tools, molds, and dies. Spring steel has high elasticity and fatigue strength, enabling it to return to shape after bending. Electrical steel is engineered for high magnetic permeability, ensuring efficient energy conversion in motors and transformers. These steels demonstrate how precise alloying can tailor properties to meet a wide range of industrial needs. Cast iron is a key ferrous alloy, with 2% to 4% carbon content, plus silicon, giving it excellent castability. Formed by casting molten iron into molds, it comes in several types, each with distinct properties and uses. Grey cast iron has flake graphite, offering excellent machinability, high compressive strength, and vibration damping, though it's brittle in tension. It's used for engine blocks, machine bases, brake drums, and pipes. White cast iron forms cementite through rapid cooling, making it extremely hard, wear-resistant, but very brittle. It's suited for mill liners, crushing rolls, and abrasion-resistant parts. Ductile or nodular cast iron contains spherical graphite nodules for high strength, toughness, and good machinability, ideal for crankshafts, heavy-duty gears, and pipeline fittings. Malleable cast iron is made by heat-treating white cast iron, improving ductility, toughness, and shock resistance, making it useful for railway gear, agricultural machinery, and pipe fittings. This range of cast irons shows how microstructure can be engineered to meet specific performance demands. Ferrous metals, made primarily of iron, have a distinct set of properties that explain their widespread use in industry. Most are strongly magnetic, making them essential for electromagnets, transformers, and motors. They are prone to corrosion when exposed to moisture, so protective coatings or alloying elements like chromium are used for resistance. Their high tensile and compressive strength make them ideal for construction, automotive, and heavy machinery. Formability depends on carbon content. Low carbon increases ductility, while high carbon raises strength but reduces malleability. Ferrous metals also have moderate electrical and thermal conductivity, balancing strength with functional performance. They are generally abundant and cost-effective to produce, making them a practical choice for countless applications. The following graph provides a comparative overview of the relative strength and ductility of various ferrous metal categories. Wrought iron exhibits a relative strength of 4 and a high ductility rating of 9. Low-carbon steel demonstrates balanced properties, with both strength and ductility rated at 7. High-carbon steel offers a high relative strength of 9, but a lower ductility of 3. Lastly, cast iron shows a relative strength of 6 and a significantly lower ductility rating of 1. Ferrous metals, while widely used across countless industries, possess a unique set of characteristics that bring both notable advantages and certain limitations. Let's begin with the advantages. First, they are readily available. Being among the most abundant and extensively refined metals, ferrous metals ensure a consistent supply at a cost-effective price. Second, they offer a high strength-to-weight ratio. High-strength steels in particular provide remarkable structural integrity relative to their mass, making them ideal for heavy-duty and load-bearing applications. Third, ferrous metals are highly recyclable. They can be reused without significant loss of their mechanical properties, supporting sustainability and reducing the energy required for production. Finally, they are versatile. Through alloying and processing, they can be tailored to meet a wide range of mechanical and chemical requirements across virtually every industrial sector. However, alongside these benefits come some limitations. Ferrous metals are prone to rust. Exposure to moisture leads to oxidation, often requiring protective coatings or costly alloying for corrosion resistance. They are also heavier than non-ferrous metals, such as aluminum, which can be a drawback in weight-sensitive applications like aerospace engineering. In some cases, their magnetic properties can be undesirable, as they may interfere with sensitive electronic or medical equipment. Lastly, at high carbon levels, ferrous metals tend to become brittle. While hardness increases, so does the risk of sudden fracture under impact. Understanding these advantages and limitations is essential in selecting the right ferrous metal for the right application, ensuring both performance and efficiency in engineering solutions. This bar chart shows the key property comparison, ferrous versus non-ferrous metals. Compares 3 properties, relative strength, corrosion resistance, and relative density across 3 metal types: untreated ferrous, stainless steel, and aluminum, non-ferrous, using a relative score scale from 1 to 10. Untreated ferrous metals show high relative strength of 8 and very high relative density of 9, but have poor corrosion resistance of 2, indicating susceptibility to rust and degradation without protective treatments. Stainless steel demonstrates balanced performance, with high corrosion resistance of 9 and good strength of 7, while maintaining a relatively high density of 8, making it strong and durable, but relatively heavy. Aluminum, non-ferrous, has moderately high strength of 8 and moderate corrosion resistance of 5, but its relative density is much lower at 3, highlighting its lightweight nature compared to ferrous metals. Overall, the chart emphasizes the trade-offs between strength, corrosion resistance, and density across metal types, showing that ferrous metals excel in strength and density, but lag in corrosion resistance. Stainless steel offers all-around performance, with higher weight, and aluminum combines good strength with low density for lightweight applications. Ferrous metals, valued for their strength, durability, and versatility, form the foundation of modern industry and infrastructure. Their unique properties enable a broad range of critical applications worldwide. In construction, steel is indispensable for structural beams, rebar, and framing systems, ensuring unparalleled strength and stability. In the automotive sector, ferrous metals enhance vehicle safety and performance, serving in engine components, body panels, and precision gears. In manufacturing, they are essential for producing cutting tools, dies, and machinery parts, requiring high hardness and wear resistance. For transportation, they provide the backbone for railway tracks, bridge structures, and the hulls and engines of ships. In the electrical field, the magnetic properties power motors, transformers, and other energy conversion devices. Even in consumer goods, ferrous metals appear in everyday items, such as stainless steel cutlery and durable appliance frames. From skyscrapers to kitchenware, ferrous metals remain integral to the progress of modern society. This horizontal bar chart shows the conceptual impact score of ferrous metals by industry. It illustrates the relative significance of ferrous metals across 6 major industries, using a conceptual impact scale from 0 to 10. Construction, manufacturing, and transportation industries each register the highest impact score of 9, underscoring the critical role of ferrous metals in structural frameworks, industrial production, and transport infrastructure. The automotive sector follows closely, with a score of 8, reflecting the extensive use of steel and other ferrous alloys in vehicle manufacturing. The electrical industry shows a slightly lower impact score of 7, indicating substantial but less dominant reliance compared to heavy industries. Consumer goods ranks the lowest at 6, suggesting that while ferrous metals remain important, they are less central to product composition and manufacturing in this category. Overall, the data highlights that ferrous metals are most indispensable to construction, manufacturing, and transportation, while their influence, though still notable, is comparatively reduced in electrical and consumer goods sectors. In conclusion, ferrous metals remain the backbone of modern engineering and industrial development. Their versatility, cost-effectiveness, and wide range of mechanical properties make them indispensable across countless applications. From lightweight structural components to hard-wearing tools, ferrous metals can be precisely engineered to meet diverse performance requirements. Understanding their characteristics is essential for optimal material selection, enabling engineers to drive innovation, enhance efficiency, and ensure long-term durability in every project. And that wraps up my virtual presentation. Thank you so much for your time, attention, and enthusiasm. I hope you enjoyed this AVP as much as I enjoyed sharing it with you. Once again, that's all, folks. Thank you, and God bless you all.